Okay, so we've generalized Z about as much as we're going to do in this class, namely to PIDs. And we saw that f adjoin x, so if we take a field and we adjoin, we look at polynomials over that field, we get a PID. So in a lot of ways, polynomials over a field and the integers, they share a lot of ring theoretic properties because they're both PIDs. We're going to turn our attention to certain special types of ideals. So let's let R be a commutative ring. An ideal, we're going to use a special font. This is called the Fractor font. So P in R, a proper ideal, a proper ideal, P in R, so it's not allowed to be equal to R. It's called prime, or a prime ideal, if it satisfies a very familiar looking expression. So if whenever you have a product, so A, B, and R are such that A, B are in the prime ideal P, we have A is in P or B is in P. So what we've done here is we take divides. So that's the end of the definition. But what this does is, so morally, what we're doing is we're taking divides and replacing it with is contained in. So we get rid of divides in the definition of a prime number, and to make a prime ideal, we use what we have, and that's containment. So, so this is kind of weird. Let's do an theorem that will give us some ways of like recognizing if certain common ideals that we've seen before are prime, and then we'll do some examples of with like our hands-on ideals in a second. But let's do a theorem first. Suppose R is a domain. So in particular, it's a commutative ring, but it has no zero divisors. And P in R is prime. And since we have a couple competing definitions with prime here, let me just specify what type of prime it is. P is an element of R, so this is a prime element. So what can we do with a prime element? Well, we can generate an ideal with that element, and I'm going to call that frac P. And math frac P is going to be a prime ideal. So that's our conclusion here. And the slogan here is prime elements generate prime ideals. Ooh, that got away from me. All right, so let's prove this real quick. Proof. Suppose we have A, B, and R are such that A times B are in the ideal generated by P, which I'm calling frac P. Well, then AB is PK for some K in R. Thus, P divides AB. And that's what it means to divides. But P is a prime element. So if I have a prime element, then it must divide A or it must divide B. So P is AM or P is BN for some MN in R. Thus, oh shoot, that's the wrong way. Whoops. A is PM or B is PN for some M in R. Then, well, what does this say? It says A is a multiple of P or B is a multiple of P. But this is, of course, what we're calling frac P. And that's exactly what it means to be a prime ideal. If you have a product, then you have one of the terms of that product. All right, we'll look at examples of prime ideals and non-prime ideals in the next video.